Welcome to The Explainer. Today, we're going to pull back the curtain on something amazing, the simple logic that builds the world's most efficient networks. We're talking everything from the internet to our power grids.
So, let's kick things off with a puzzle. It's a puzzle that, honestly, tech giants and city planners wrestle with every single day. Imagine this. You got a bunch of points you have to connect, but every single connection has a cost. So, what's the deal? How do you link everything up for the absolute rock-bottom lowest price?
All right, let's get into it. Here's how we're going to tackle this. We'll start with the puzzle itself, define what a perfect network even looks like, then check out two genius algorithms for finding it, primes and Kruskals. We'll see how they stack up against each other, and finally, where you can find these things out in the real world.
Okay, first things first. Before you can build anything, you need a blueprint, right? Well, in the world of computer science, the blueprint for the most basic, most efficient network has a name. It's called a spanning tree.
So, what is that? Think of it like this. A spanning tree is the no-frills, absolute bare-bones network. Its job is to connect every single house, yeah? But it does it using the fewest cables possible. And here's the crucial part. There are absolutely no wasted connections, no redundant loops. It's just pure, unadulterated efficiency.
And you know what's really cool? The math behind this is just elegant. It's beautiful. So if you have, say, a bunch of houses, let's just call that number V for vertices, you need exactly V-1 cables to connect them all. No more, no less. If you add even one more cable, you create a wasteful loop. And if you have one less, well, someone's getting left off the network. Simple as that.
Okay, but here's the thing. We don't just want any old spanning tree. We want the cheapest one. Because in the real world, every cable has a cost, right? So now we're hunting for something specific, the minimum spanning tree, or MST for short. And that's it. That's the one spanning tree that adds up to the lowest possible total price. This right here is the holy grail of our puzzle.
All right, so how in the world do we actually find this perfect network, especially when there are tons of possibilities? Well, let's meet our first tool for the job. It's a really clever and intuitive method called Prim's algorithm.
You can think of Prim's algorithm as the neighborhood grower. It's like a really methodical builder. It starts at just one house, and then it patiently grows the network outward, one connection at a time. And at every single step, it always picks the cheapest possible connection to a new house. The process itself is beautifully simple, seriously. You just pick any house to start, doesn't matter which one. Then, you look at all the connections from your little starting network to a house that isn't connected yet. You pick the absolute cheapest one. Bam. Add it. Now your network is just a tiny bit bigger, and you just repeat. You just keep making that simple, greedy choice. Find the next cheapest link over and over until every single house is on the grid.
Okay, so that's one way to do it. But now let's check out our second tool, which tackles the exact same problem, but from a completely different angle. This one takes more of a bird's-eye view of the whole situation.
So, say hello to Kruskal's algorithm. If Prim's was the grower, then Kruskal's is the bargain hunter. It's super savvy. Instead of starting in one spot and growing, this algorithm looks at every single possible connection in the whole neighborhood, all at once. It's like it has a master spreadsheet of all the deals.
And its method is just as elegant. First, you list out every possible cable you could lay, and you sort that list from cheapest to most expensive. Then, you just go right down the list. You pick the cheapest connection. Does it create a loop with what you've already built? No? Great, add it. Yes? Okay, throw it away and move to the next one. What's cool is that at the beginning, you're not building one network. You're creating a bunch of little disconnected islands, a forest of tiny trees, if you will. And as you keep adding the cheapest links, those islands eventually all connect up into one perfect network.
So there you have it. Two totally different but equally brilliant methods. We've got the grower and the sorter. And here's the amazing part. They both guarantee you'll find the absolute cheapest network. So the obvious question is, which one is better?
Well, you know the classic answer, it depends. It really comes down to the kind of network you're building. Prim's algorithm, our grower, is fantastic for dense graphs. Think of a busy city center where there are tons of possible connections. Kruskal's, our sorter, on the other hand, really shines with sparse graphs, like connecting towns in the countryside where things are more spread out and there are fewer connections to begin with.
And if you peek under the hood, they each have their own clever trick to stay fast. Prim's uses this special kind of to-do list, technically called a priority queue, which is awesome because it always keeps the next cheapest connection ready to go, right at the top.
Kruskal uses a different system, something called disjoint sets, which is basically a super fast way to keep track of which houses belong to which little island network. That way, it can instantly tell if adding a new cable would create one of those pesky loops.
Okay, so this has been a really cool computer science puzzle. But you might be wondering, does this stuff actually matter? Is it just a theoretical thing for textbooks? Oh, no. It's so much more than that.
Check out this number, over $1 trillion. And that's a conservative estimate of the money saved in designing infrastructure around the world, all by applying these simple ideas. It's incredible, right? By using what we call a greedy approach, just always picking the best immediate option, we end up building these unbelievably efficient systems on a global scale.
So here's the real takeaway. This logic, it's everywhere. It is the invisible backbone of so many things we take for granted. We're talking about the design of your office's computer network, the entire electrical power grid for a country, planning out roads and railways, even designing the tiny, efficient circuits on a computer chip. It's the hidden blueprint that saves an unimaginable amount of money and makes our world work.
And that brings us to a really interesting final thought. Remember how we called these algorithms greedy? They just make the best, most obvious choice at every single moment. They don't plan 10 steps ahead. And yet, in this case, that simple, short-sighted strategy leads to the most perfect, most efficient overall result. It's kind of wild. It makes you wonder, doesn't it? Where else in life does just picking the best immediate option actually lead to the best possible outcome in the long run?